Okay.
All right. Recording is in session. Let's begin.
Mr. James is going to give his presentation. It'll be about 20 minutes long. Before we start, everybody please sitting down and quiet looking forward.
What all have we learned already about spring?
That's okay, Ryan.
I wasn't here for all the days that you guys were doing spring, so just shout out some stuff that you know.
They stretch.
Huh?
They stretch.
Straight stretch.
There's force.
There's a force. What kind of force?
Tension. Or spring force, whatever.
Spring force. We'll go into a little bit more about that.
Spring force scales linearly.
Force scales linear.
Yes, linear.
Okay. Term 5, whatever. Anything else? Yeah.
Restoration force.
Restoration force. Thank you. That's a big one for this one. All right. So we know that they stretch, that they have a force when they stretch, and that force scales linearly, and that force is called the restoration force. All right. Any questions before we continue? All right. So let's just go ahead and get started with a special video I have here for you guys. It will be an interesting scenario based on how springs work. So before we begin, let's just take a look at this image. He's holding himself a spring, it's off the ground, and it's at basically full stretch. You can see at the bottom here it's not quite properly stretched, but it's close enough. So when he drops this, what do you think is going to happen?
It'll hit the ground.
Well, yeah, it'll hit the ground, but in what motion do you think it'll hit the ground? Do you think it'll fall in this extension and just the bottom will hit first, and then it will start collapsing as it hits? What do you think?
It'll shrink and then bounce off the ground.
Bounce off the ground? That's an interesting one. But the important part there, you think it'll shrink before it hits. Okay, why do you think that?
Because not only is it falling, but it also has the other force contracting on it.
Interesting.
But
Well,
as it falls, time goes on, they're both gonna.
so let us see what happens when it's in action. That's crazy.
Really slow. It's gonna shrink.
Oh, you're right, there's a little bounce there. I think that's just because it's a springy metal instead of it being That's just another bigger example. So, that seems like magic, right?
Yeah.
First time I saw it, I was bewildered. I had no idea what was going on.
May I make an observation?
Sure.
That was cool.
That's what's cool. That's why I wanted to use this as my thing to show. So, I guess we'll show the other examples as well. Just have an even more extreme version. See how the bottom basically isn't moving at all. It's still in the same spot as before. Think about when it is that the bottom starts to move out. Only after it's completely collapsed does it actually start falling as a whole unit.
Wait, I want to see that one. That looks cool.
Sure. It's just the same drop from a different perspective.
That perspective looks cool.
Because the restoration force is greater than the weight force.
Look at him. Look at him.
So if you lift it on the ground and remove the ground, it will float for a second before it falls.
That's a really big swing, by the way. I've never seen a swing that big. I'm out of school. I think the steps you have to be in order to bounce that thing. You guys don't get to explain, that's my job today. All right. So,
Oh, okay.
seems pretty miraculous,
Yeah.
but there's an easy explanation for it. We're going to try and solve it. So, since there are two different parts to the spring, basically, from what we saw of how it's acting, I'm going to draw the two different parts. I'll just start drawing really quick. It's worse indoors even. So, here's the top. Here is the bottom. Has two different diagrams. So, when he's holding it, before he releases it, what forces are applied to the top and the bottom?
Natural force and gravity.
Natural force? Is it on a surface anywhere?
He's holding it up though.
Yeah. So he's got a force holding it up, force of, let's call it the hand. And then obviously gravity's pulling down the spring, right? So we've got gravity pulling down on the string. Over here, we've got force of gravity pulling down on the spring. And we have another force holding it up, but what is this force? Spring force, or the restoration force as you call it, but we'll just call it the spring force. So when he's holding it like this, perfectly in equilibrium, it's not moving anywhere, it's just perfectly stationary. But let's go ahead and show the moment that he lets go of it, erasing the hand. So now, the top only has the force of gravity pulling on it, so naturally it does what? Starts falling, yeah. But over here, this spring force is still active. So that means that this part isn't going anywhere. It's still in equilibrium. And it's only after the top gets close enough to the bottom that the force of the spring is done restoring itself. And then you have the force of gravity pulling the whole thing down. That's why it seems to just hover in midair, as if it was not, doesn't have gravity applying to it at all. Pretty cool, right? So, let us use this example to try and explore a few other situations with springs. I have one in my pocket here. Show a few. Most of these should seem pretty familiar to you, since you've already seen them in the past, just with things that aren't springs. So we've got a mass here at the bottom, hanging off of a spring. This is basically exactly what you were doing in the spring forces lab a few days ago. So, what are the forces on this?
Mass.
Force of mass. Hold on by gravity. And what's this force? Spring force.
Restoration.
Yep. We'll just call it force of the spring. So, this isn't going anywhere. It's in perfect equilibrium. So, but what happens if we remove the mass, for instance? Just get rid of this. What happens? Collapse into its more collapsed state. I'm sure a lot of you saw that when you were in the lab. When you took the hanger off, it just fell back into its collapsed state. A note, by the way, I noticed and practiced with those springs, but their restoring force is a lot stronger than the force of gravity on them, which is why even when they're hanging, they're full of flow. So unfortunately, I couldn't use those to demonstrate that physically in the classroom here. Just making a note of that as an interesting little note. So different springs can have restorative forces that are stronger or weaker than oil. All right. Situation number 2. This is going to be another hanging one. But now we've got 2. Don't worry, you've already worked with problems like this. I've seen you do them. So we've got a mass here. We've got 2 springs. Let's say for the sake of argument that both springs are exactly the same. Got the same spring force, same storing force, everything. So let's list some forces again. Well, it's not quite tension. It's more like the spring force, but
Restoration.
And we've got force coming down. So based on what we've seen from previous force by diagrams, what do we know about this force versus these 2 forces?
It's only force.
What do we know about how strong these forces have to be in relation to this force?
This is equal.
Because right now, this isn't moving anywhere. We're bouncing it. But what parts of these forces are the same as this combined? Remember how we have to, what's the word that Mr. Blank likes to use? Quantumania.
Yeah.
I don't think anyone likes to use
What's
that word.
amazing?
So, no, the word he likes to use is resolve the forces. So we have the force of the spring in the X direction, and the force of the spring in the Y direction. Now, since it's not moving horizontally, do we know that these two horizontal forces, what's true about that? When you add them together, they're zero, because they're equal, but they're in opposite directions. And what do we know about the two vertical spring forces? They're also equal. But since they're both pointing in the same direction, that means they have to be equal to the force of the mass, right? Alright. So what happens, this is a bit more of a complicated one. What happens if we get rid of the mass at this time? It's true, they'll collapse up in this way. But now they have a force pulling them to the left, and there's nothing pulling them back to the right. So what direction do you think they're going to fly into as they're restoring themselves? So this one will go to the left, this one will go to the right. So you've got a little bit of spring back and forth here as it collapses itself back into shape. Alright, number 3, back to a simpler option here. So we've got ourselves a wall, got a spring attached to the wall,
I'm over it.
and we've got a block attached to the spring. Alright, let's search mass to it. So let's label ourselves the forces acting on this block. Force of the spring on the box?
Yeah.
Okay. Force of the spring, drive the box to the left. We've got our usual friction.
Gravity on the ball. You say friction.
Gravity,
Normal force, since the box isn't going in the vertical direction at all. Now, I could write a few different forces here, depending on what I say about how effective the mass of this box is. If we say the box isn't moving, then that means that there has to be a force to the right holding it in place, and that force would be what usually keeps objects in place if they're not friction. So, if the box isn't moving, then these two are equal. Yeah, if you ever want to show that two different arrows are the same magnitude, you can just draw a little arrow like that. And that will show, that's a way to basically designate that. It can be generally used for this. So, if the box isn't moving, we have the force of friction is equal to the force of the spring pointing to the left. What if the force of friction isn't equal? If it's lesser?
Then it'll start going this way.
Yeah, you'll start moving into the box. The box will move into the wall until the spring has its restorative force complete. And of course, if we have the old situation, remove the box entirely, and the spring will just rapidly coil back into the wall. So let's draw the box again. And ourselves a slightly different situation. Now, I've got a rope that I'm pulling on the box with. So we've got force of tension. We'll leave the vertical forces over here because we already know what they're doing. So, if the box isn't moving, then what do we know about this and this? Okay. Easy enough to say they're equal. Yeah. And if the force of the pull is weaker than the spring, so like if this is greater than this, go into the wall as the spring restores itself. Now, here's an interesting version of it. if I just say that this is at its resting point, if it's already fully compressed, and then I start pulling on it with this force so that it starts stretching. At what point so obviously there's going to be a force pulling on it, it's going to be accelerating to the right. But at what point will it no longer have an acceleration to the right, assuming I don't overpower it? Yeah, when the spring is stretched enough so that it goes back to the case. It goes back to the case where it's equal to that. Now, obviously, you could pull even harder and start stretching the spring to the point you damage it, which I believe you warned them not to do that. But in general, if you're pulling on a spring like this, you can pull it to the point where the restorative force here is equal to the pulling force, and then you'll no longer have an acceleration unless you keep increasing this. Isn't that how garage doors work, more or less? I know a lot of garage doors have a spring like that one does.
Yeah, it's the torsion spring now.
Yeah.
It just uses the force.
Force of gravity.
Good for
This one is more of a general case that you guys should have the words stuck in your brain by now from him repeating them to you often enough. The box.
No,
You
man.
got the spring, say it's attached to just a thing up here. So, the box isn't moving, what forces do we have?
Wait, is the box moving or no?
That box is not moving.
Is there friction?
The friction and.
MG sign.
So,
Milligrams.
MG sign thing. Okay, so the component of gravity along the ramp, which one would the component of gravity along the ramp be?
MG sign.
Sign thing. Okay.
Milligram.
Theta, that is not milligrams, unless the box is really small. Very small box, milligrams, dang. And so the force of gravity into the ramp would be cosine theta. Got the usual force coming out of the ramp of what? Normal force. And we've got, this force is what again? The force of the spring or the restoring force? Alright. Where would friction be? Would it be going up or down the ramp?
It's going the opposite way of MG sign.
Yes. Why would it be going off the ramp, bro? It's going up the ramp.
Bro, it's friction. So get on my level. You're not in calculus. You don't know.
There is no friction.
This isn't calculus.
If it's not moving, then there's no friction, right? Because there's already a force holding it up against the force of gravity, so it's not going anywhere.
Well, what if the spring force is
Talking
larger
about
than the force of gravity?
Oh, the string force is larger than the force of gravity. Then you'll have the friction acting against the spring force as we go down. All right, so that's a few different cases. Now I'm going to draw the force cases again, and I want you guys to just pull out a random piece of paper and label them like I just showed you.
Piece of paper. I don't know. You're the one.
And I'll just put some random numbers on here, and I will see if you guys want to say if they are in equilibrium or not.
This isn't big enough. You get it.
How much bigger do you want, Travis?
You need a big piece of paper.
This is the most I've got.
Mr. James,
Yes.
do we need a big piece of paper?
However big you know that you draw, a single blank sheet of paper should be
What your reward, Travis? What? Would you?
He gave you that, I think that's not enough. One sheet of paper should be enough.
3 inches is enough.
What did you say, Chris?
Class, man. We're in a class right now, dude. Alright, dude. Give me Travis. Where's Travis?
That's too much.
Too much.
Oh, hot.
Froze out like a light.
I'm just snack.
Are you good, Nick?
We're doing an experiment, by the way.
Wake up.
Bro, that was on me.
Nick, how's this gonna go?
No, Trish. There's a camera right behind me.
Don't mess with me.
Threw a water bottle on my head. The T word. Oh. I'm 50 water bottles.
Wait, so what do we need? We need to draw that?
Yeah, you'll just draw each of these cases, and using the numbers I put up, you'll say if you think it's an equilibrium.
Travis, can I work with you? I don't have a piece of paper.
No.
That's my number. Work with you.
No, I said. Yeah, you have to bring a piece of notes.
And for the record, because I'm not your teacher, no, obviously this is not for a grade. This is
Oh,
just practice.
What, it's not for grade?
Nope.
What? Me? I can get you something. You guys woke up next, so I think it's. Should be.
Yeah, that's the next one.
Let the poor man sleep. Bro was on a heist.
If you can't read my writing, just let me know.
Can you draw a line between 1 and 4?
It's just the division of that line.
You.
So are you asking for the 1 and 4? Or just overwhelming?
I can't. What does he say?
Just if you think it's an equilibrium.
Or overwhelming?
What did he say?
What?
What'd you say? Who does?
Who is that?
Asian does?
What?
Jeez,
What did I do? He doesn't kid. Wait. Here? Here?
No, I was back.
Oh, it's in there. Okay.
What do you, we could do for the backpack?
Trying to find gum. Oh, he has gum. No, he don't.
Just in case it's hard for those to.
Two zeros, they're doing
If you have 2 zeros, but not gum.
Right. Should be all good. And we'll take like a minute or two to give you guys some time to work on this. Again, I will ask for volunteers to come up and just write an E next to it if you think it's an equilibrium, or an E if you think it's not equilibrium. So take a minute or two for that.
Where did they go?
On the board space, you can hit the white button on the TV screen and choose the board.
True, I should
It's
have
up to you.
done that.
Up
But
to
I
you.
forgot.
I should have told you.
It's fine.
I completely forgot about writing on the board until just now. Also,
Yeah. Let's see.
The problem on number 30, not 15.
Oh. 24 minutes, 30 seconds.
oh, I'm over time. Okay, that's fine. We'll just finish off with this then. Well, no, I'm over time. Fine. It needs to be a minimum.
Subscribe to D3 the back.
It's one of those things where you never quite know how much time you're taking on a lesson until you're done. You know, I've noticed that with you.
Yo, hey.
Alright. Does anyone have an answer for 1?
I do.
Alright.
Oh,
left one, right, what you think?
Oh, I did. Oh, shoot.
E for equilibrium, and N for nothing.
dirty ass
Alright, so it's an equilibrium, you say?
Yes.
Well, that's fairly simple because there's 10 force going up, 10 force going down. It's stable. Alright, number 2. Do we think number 2 is an equilibrium? Does anyone have an answer to that?
Oh, I got it.
Okay.
Yay.
Yay.
I like your shoes.
Not.
Yeah.
Anyone want?
Yeah. Oh, because 2 plus 2, no, you got 2 in here, so 2 plus 2 is 4, and there's 5. And so 5 minus 1 is, 5 minus 4 is 1.
So we'll start to go down a little bit, presumably until it reaches the point where these forces will increase and then it will be equilibrium.
Yeah.
There might be a little bit of balancing involved.
What? That was a good lesson.
Sure.
Yeah.
Just wanna get you.
I volunteer, dude.
What's with the notes? Yeah, you worry about the notes?
Actually, kind of back there, so. Oh, yeah, never mind.
Yeah.
This is
Yeah,
not
John.
even-
Not equal this. Well, that's fair
That's
enough.
15 and 5.
Be down. So it'll be pulled into the
She
wall.
just wanted to be in the video.
So, number 4. I realize there's not a lot of space, so let's just put it right here. Anybody want to do a number 4?
I'll do number 4.
Travis.
Already done one,
you're
but
not-
if no one else volunteers,
I volunteer, Kyle.
he volunteers.
Dang it.
Number 4.
Guys,
So it is equilibrium, because we've got 15 going to the left. We have 5 of the friction of the first one, add 10 of the string pulling on it, so it will stay in place. And last one.
I volunteer, Kyler Murray, or whatever his last name is.
Karaka?
Yeah, the dude with the glasses.
Tyler
You
Karaka.
can do it if you want, if you feel confident. It's
No,
pretty
he's
simple.
I think Jared wants to.
There you go put it.
No! Those are the Pilgrim 11s!
Somebody has all told us up.
Those are the Pilgrim
It
11s.
is equilibrium. Okay.
Those are Birkenstocks.
5 for 5. We got great answers on
There's
that.
the
All right.
duplicates.
Yes.
Don't mind this puzzle, everyone think that they've got more or less the idea of the body diagrams and
I think
springs.
so.
Ready to go.
160.
Glad to be of help. Now I just
No,
pause
160.
the video. I turn things back over to you, Mr. Quinn.